Okay, so this is our network architecture. So our service objective is to send a stream of packet datagrams from a single sender to K out of N receivers on a network. Choose best K out of N destinations. Routing protocol chooses the best multicast path. And in the figure we drew on the right, it shows a host which is trying to send a packet datagram to two other hosts in the network. So these are our topology assumptions. No more than 256 hosts with a max of 50 routers. Unreliable network with packet loss probability per link of P. Each N node is attached to only one router. All links have the same characteristics. For example, hop cost is 1 and same MTU of 1500 bytes. Hosts have static 8-bit addresses. A host cannot be the direct neighbor of another, and no network failures. So this is our protocol concept. The service provided is K out of N multicast for packet datagrams. Our packet structure is OSPF packets, which we go into more detail in the next slides. The control plane, the link state protocols, which is the link state request and link state update, IGMP, go back, and ARQ. For the data plane, you have K values, sender and recipient IP addresses are stored inside packets, and we use Dijkstra's shortest path tree used for finding the routes. So this is our the packet formats for OSPF header. All OSPF packets share a common OSPF header of 24 bytes, which allow the receiving router to validate and process the packets. The format of the OSPF header we are using are smaller without area ID and authentication type. So we use version 2, which is 1 byte. And then inside the packet, we have the type, which specifies the type of OSPF packet. And there are 5 different types. The hello packet, link state request packet, link state update packet, and the link state acknowledgement packet. The packet length provides the total length of the OSPF packet, which is 2 bytes, the router ID, and the checksum. So this is the hello packet. So the hello packets are OSPF packet type 1. The whole packet is 32 bits long. The network mask is the subnet mask of the advertising OSPF interface. The hello interval is the interval at which hello packets are advertised. Options is where the local router advertises its capabilities. RTR, PRI is the priority of the local router. The router dead interval is the dead interval as requested by the advertising router, and the designated router is the IP address of the current designated router. Next, we have the link state request packet, which is OSPF packet type 3. The link state type is the type of LSA requested, which is 4 bytes. The link state ID depends on what type of LSA, which is also 4 bytes. And the advertising router is a router ID of the requesting router. And then next we have the link state update packet, which is OSPF packet type 4. These packets implement the flooding of LSAs. Each LSA contains routing, metric, and topology information to describe a portion of OSPF network. So the number of LSAs is the number of LSAs within an LSA packet. And then next is the complete LSA, which is encoded in that field.
All right, so thank you, Nicole. We're also using, since we're using link states, we're also using a link state acknowledgement packets for our OSPF packet, which is of type 5 in this case. OSPF requires acknowledgement for the receipt of each LSA. Multiple LSAs can be acknowledged in a single LSA packet. We're using an LSA header packet, and we're also using like the typical LSA packet. We're gonna leave out on the link state checksum, like you guys discussed before with other groups, because we don't really need to check for errors. And we also using the multicast data packet, which is like a typical multicast data packet we're using for now. We also using the sequence number for checking routes and stuff. Um, we are for continuing from the packet formats. We're also using IGMPv2, where we're storing the type, max response time, and group address. Then again, we're leaving out on the checksum because we don't. We're assuming that there's not going to be any link failures and errors in the network. We're also using a control packet with multicast group ID, value of k, and sender's IP and control data for pairs of routers like R1, R2, R2, R3, and stuff like that. For a routing algorithm, we're going to be using hello messages, join messages of type IGMPv2, and the multicast extension of link state protocols, which is MOSPF, MOSPF basically, at each router that are connected to hosts. To find the best k out of n, we're going to sort the distances between nodes in ascending order, then choose the topmost 2k nodes that belong to the correct multicast group, and then relax all the nodes according to Dijkstra's algorithm. Here's a typical example of an iteration of Dijkstra's algorithm with like 4 vertices and a bunch of edges / lengths. I'm not going to go through this ugly looking table. Here's the continuation of Dijkstra's algorithm. Here's a MOSPF free table we have here. And the complexity of Dijkstra's is the n log n plus L, where n is the number of nodes we have, and L is the number of lengths / edges. Here, so for data plane forwarding, here's examples of 3 routing tables for routers R1, R2, and R5. The paths we drew, the paths we considered here are from one router to another, and our source here is S. And for k equals 2, I believe, we'll discuss that in the example later on. But yeah, there's an example. Here's an example of routing tables for 3 routers. And for data plane forwarding, our network design is using a copy forward mechanism where each router will have a smaller buffer in order to facilitate the hold of each packet before they're copied and sent to different destinations. There's a mechanism where like the host doesn't have to do too much processing in order and just leaves the copying of data packets to the routers itself. Here's an example of forwarding of packets through a router with like 4 ports. The data is coming in from port 0, and the router is copying and forwarding accordingly through from port 1 through port 3. Here's the example networks given to us. So for network 1, we showed k equals 2 and k equals 3. For this network, it doesn't matter for k equals 2 if you send it to D1 or D2 or D2 or D3 or D1 or D3, because the network is kind of similar, symmetrical from throughout the path R1, R3, and R6. And to the right, we can see the diagram for our network for k equals 3, where the sender sends data, 3 copies of 1 copy of the data to R1, which it replicates into 3 copies of data and sends it to D1, D2, and D3. And for network 2, we just did k equals 2, where it chooses the best 2 out of the 3 destinations we have. For example, if we chose the route R1, R3, R4, and then D1, it would have been like harder for the method for our protocol to send the data to D2 again, because if we send the data from R1 to R2, it's easier for R2 to copy the data twice than it is for R1 to copy the data twice right here and then send it to R3 and R4, then again to R2. And this is like the best k out of n possibilities for k equals 2 we drew here. And for a summary, we just summarized the key protocol designs we mentioned in here. Every node in the network has separate tables. The router has separate routing tables. The router path trees are set before the multicast implementation. So according to Dijkstra's, so for performance, our Dijkstra's algorithm will be n log n plus L, like we discussed before. And for sorting the links, we're using heap sort, which has complexity of n log n. Yeah. Any questions?
So you are maintaining complete routing information at all these places. Can you go back to your routing tables?
Yes. There you go.
Yeah. So you have an assumption is that whatever is the path, the beginning of the path, the router beginning to the path of like the beginning of the path is the router which is your next hop also, right? So for R1 you will maintain R2 R4, which is like R2 is your next hop for that
Yes.
destination.
Yeah.
Okay. So you don't need an extra table entry for the next hop, which is fine.
Yeah.
Just that I would like to know like what data structure you plan to use to maintain this path.
For that, I think we're planning to set the routes beforehand before we multicast to like the different destinations. So we're gonna store the routing tables inside each router using, I guess, IP addresses and like data IP address packets inside the router. Like so for let's say let's go back. So for path R2 R4 for reaching destination 1 from source, we would use we would store at R1 that the next hop would be R2, and for R2 we would store the next for the next path to be R4, which is obvious in this example right here.
Okay.
Yeah, we're gonna use 8-bit addresses.
Okay. Okay. Yeah. I just want your key will be destination, right? Like so if you are storing
Yes.
something like a
Yeah.
dictionary, your key is destination. Okay.
So if I understood your scheme, you are looking at every pair of D1, D2 and putting them into the routing table as an entry. Is that correct?
Yes. Like for example, for interface 1, we have D1, I mean, for both the interfaces we have for pairs of for a pair of destinations, for all the destinations basically. So for D1 we have the path from R1, R2, and R4. For the routing table of R1 we have R2, R4 as the next hop, or the path, the total path basically. For D2, D3 we have, then for interface 1 we have the path R3, R5, R6 from R1.
Yeah. Okay. So I'm just trying to understand how did you choose the optimum entries for those cases where you have more than one, like for the ones which are just like D1 that comes out from Dijkstra. But for the second entry, for example, you have D2, D1. It's a bit hard to read. D2, D3, say.
Okay, so for D2 and D3, since they're connected to the same endpoint router, the path is going to be the same.
Yeah, that is true in this example, but you don't know it a priori. So do you have automatic?
No, for different destinations, we will have a different entry of the table. I just did it for the space crunch in here.
Okay, no, that's fine, and it's good to work through an example like this. I just was wondering if you have arbitrary network and you have these D2, D3 pairs. The problem you have is to come up with an algorithm that gives you the best path to the joint best path to these, right?
Right.
And the examples you worked it out, but just make sure that your algorithm is general enough. So with this example network 1 that you've put up,
right,
most of the conventional heuristics will push you to take 3 different paths or 2 different paths, whereas the better strategy is to go shoot straight down to R6. I guess that looks like R6 to me, the one on the
right. Yeah, this one is R6, yes.
And distribute locally. So if you know how to do that automatically, That's good. But I just want you to also pay attention to that issue.
Right. For this example network, this is kind of symmetric around that R1, R3, R6 path, so it's not going to matter that much. But for general purposes, yes, that might be a problem. We have to figure that out, I think.
Right. So one of your the other proposals has an algorithm which is provably close to optimal, but
Right.
that too has its complexity. So we can see how things compare as we go along.
Right.
And there are some, as I mentioned to another group, there are some interesting heuristics that tend to reward staying together as long as possible.
Right.
So that's one way you can achieve those goals. Okay, so that's good. And let me understand your packet structure again. What is your packet?
So we're using link states. So
okay,
we
more or less simplified standard OSPF packet for the control, and for the data packet, what did you show?
Data packets.
This is the IGMP.
Hold on. Wait. So here's an OSPF header. I think we're yet to like sum up what our actual data packet would be.
Okay.
That's why we didn't like come up with like, because there's some things we got to eliminate from like the routing packets too. Like for example, link state checksum, we have to eliminate that because we're assuming the network wouldn't have any failures. We confirmed on the control packet too, but yeah, we yet to implement that data packet yet.
Okay, so put that into your notes and try to simplify what you have, and particularly you don't need the IGMP protocol, so let's simplify by having a data format that can include more than one destination address.
Right.
So have you guys worked on the reliability part?
The reliability part, I don't think so. We did. I don't think we did. No.
Okay. And the other question I had was about the forwarding table. Do you guys have a forwarding table built up somewhere?
A forwarding table? No, we only have routing tables for now.
What is this data?
So I mean, like this is kind of an example of the forwarding table, I guess.
I see something like data plane forwarding slide.
Oh, okay. I mean, this is kind of like a small, like vague example of what the forwarding table look like.
Yeah. So actually,
so we're using copy forward for routers.
Right. Because you guys have routing tables which have all the information, but that doesn't tell us like how would you converge or which paths would you actually choose when you want to send. For example, when I want to send to D1, D2, D3, all of them, and from router R1,
Right.
from this should come out from the routing table that these are the paths these are the routers those would take part.
Right. Yeah.
Okay.
Probably you might have to work on some algorithmic details there, that how would you actually choose the paths from your design of whatever routing table you have just explained.
Right. Got it.
Okay.
Can you tell me how I can change to like a different screen share? Like if I want to share my
Did you share your whole screen or just this presentation?
Just this presentation.
Oh, you can just close it and probably share again with the